Welcome back to another EEG learning package from Professor Mohammadi's teaching archives. Today, we will review an important and often under-recognized normal EEG phenomenon known as alpha squeak. This infographic summarizes the definition, physiology, historical background, EEG characteristics, developmental features, differential diagnosis, and practical interpretation pearls related to alpha squeak in clinical neurophysiology. Let us begin with the basic concept. Alpha squeak, also called the squeak effect, is a brief transient acceleration of posterior alpha activity that occurs immediately after eye closure before the stable posterior dominant rhythm becomes fully established. Importantly, alpha squeak is considered a normal physiologic EEG variant and not an epileptiform abnormality. The infographic demonstrates the classic sequence: eyes open with alpha blocking, followed by a brief burst of faster alpha activity, and finally the stable posterior dominant rhythm. This transitional burst usually lasts less than 1 second. Now let us discuss why it is called alpha squeak. The terminology originated during the era of analog EEG machines. Early electroencephalographers observed that immediately after eye closure, a brief burst of faster posterior alpha activity appeared on the EEG tracing. This abrupt acceleration produced a distinctive visual pattern on paper recordings and sometimes even a characteristic chirp-like sound during analog audio monitoring. Because of this brief, sudden, squeak-like appearance, the term alpha squeak became widely used in EEG interpretation. The phenomenon reflects an abrupt onset, very short duration, transient higher frequency, and the characteristic visual and auditory impression seen on older analog EEG systems. Now let us examine the typical EEG characteristics. Alpha squeak occurs in awake, relaxed individuals immediately after eye closure. It is maximal over the posterior or occipital regions. Initially, the rhythm is slightly faster than the later stable alpha rhythm, often around 10 to 20 Hz, before evolving into the patient's ordinary posterior dominant rhythm. The duration is usually less than 1 second. Like the normal posterior alpha rhythm, alpha squeak attenuates with eye opening or alerting. Most importantly, it is a normal physiologic phenomenon. The infographic next reviews age-related characteristics. Posterior dominant rhythm maturation is strongly age-dependent. In early infancy, posterior rhythms are slow, typically around 4 Hz. By 1 year of age, they usually reach 5 to 6 Hz. By approximately 3 years, the rhythm approaches 8 Hz. Around 9 years of age, it becomes approximately 9 Hz, and by adolescence reaches about 10 Hz. Because alpha squeak reflects transient acceleration of the posterior rhythm, it may be more conspicuous in children and adolescents, while the posterior dominant rhythm is still maturing. Children generally demonstrate higher alpha amplitudes, greater variability, and broader frequency ranges compared with adults. Next, let us review the clinical and research importance. Recognition of alpha squeak helps prevent EEG overinterpretation and diagnostic error. 3 important pitfalls are highlighted in the infographic. First, the interpreter may overestimate alpha frequency if the transient squeak is mistakenly included in the alpha measurement. Second, the brief physiologic transition may be confused with abnormal fast activity. Third, inexperienced readers may overcall epileptiform or ictal activity. The infographic also emphasizes that alpha squeak may influence quantitative EEG analysis if automated frequency measurements include the immediate post-eye closure period. Now let us compare alpha squeak with other EEG phenomena. Normal posterior alpha rhythm is stable and sustained, whereas alpha squeak is only a brief transient burst occurring before the stable rhythm develops. Slow alpha variants are lower frequency subharmonic rhythms that are not specifically tied to eye closure. Fast alpha variants may resemble alpha squeak because both can contain frequencies between 16 and 20 Hz. However, fast alpha variants may persist intermittently, whereas alpha squeak is extremely brief and time-locked to eye closure. Phi rhythm is a brief occipital delta phenomenon occurring within 2 seconds after eye closure, but unlike alpha squeak, it is much slower in frequency. Drowsy alpha transition differs because it is state-related, more diffuse, longer-lasting, and associated with drowsiness. The infographic also highlights Bancourt's phenomenon. In the attached educational material, Bancourt's phenomenon refers to unilateral failure of alpha blocking with eye opening. Unlike alpha squeak, which is benign and transient, Bancourt's phenomenon is usually abnormal and may suggest occipital structural dysfunction. Now let us focus on differentiating alpha squeak from Bancourt's phenomenon. Alpha squeak is a normal physiologic variant, triggered by eye closure, bilateral and posterior, reactive and very brief. In contrast, Bancourt's phenomenon involves failure of alpha blocking during eye opening, persistent unilateral posterior alpha activity, and possible association with structural pathology. The infographic also provides practical diagnostic criteria. Alpha squeak is most likely when the phenomenon occurs immediately after eye closure, is posterior dominant, lasts less than 1 second, begins at a slightly faster frequency, evolves into stable alpha rhythm, and retains normal reactivity. Features arguing against alpha squeak include persistence, lack of reactivity, focal asymmetry, clinical correlation, evolutionary rhythmic changes, or impaired consciousness. The key teaching points are extremely important. Do not include the first half to 1 second after eye closure when calculating alpha frequency. Always interpret EEG findings within the context of behavioral state, reactivity, timing, morphology, and the overall clinical picture. Finally, the take-home message. Alpha squeak is a brief, benign acceleration of posterior alpha activity occurring immediately after eye closure. Correct recognition prevents misinterpretation, improves EEG accuracy, and helps avoid overcalling epileptiform abnormality. Understanding normal EEG variants remains one of the most important foundations of confident EEG interpretation. Thank you for listening.